So let's get things running. So let me go back to PowerPoint and start the PowerPoint, and we'll be coming back and forth to various demonstrations throughout the 3 or 4 hours of this evening's entertainment. Yeah, that's right, yes. So I'll be giving a short introduction, and before talking about cosmic rays, just to give context, I'll be talking about radiation from the Earth. In other words, radioactivity on the Earth, to give us a context for cosmic rays. Cosmic rays have been around for, well, forever, but our understanding of cosmic rays started about 100 or so years ago. Then I'll be telling you about how we can detect cosmic rays, some of which of the detectors are on this table. And I'll be finishing with thinking about where are these particles actually coming from. Saying that they are raining down on the Earth is one thing, but where do they actually originate? What is the source of these particles flying through space? And then I'll summarize at the end. I've talked to the BASoc lawyers, and they insist that I make this following statement. This talk will include a number of demonstrations which will include radioactive samples. One of the radioactive samples is a banana. Yes, these things are radioactive, and I'll explain why later. I have a few other samples that I'll be using. At the end of the demonstrations, I'll be putting those to one side, and I will then invite you to come more close and have an inspection of the front table. I'm keeping you at your distance at the moment, just to keep you at least 1 meter from the samples. The radioactive samples that I've got are all naturally occurring samples. They're bits of Earth that have been dug up, and they pose no risk to any members of the audience. Okay, just to make that absolutely clear. Okay, on the front table, there's a couple of radioactivity or radiation detectors that in principle can pick up cosmic rays. There's a so-called Geiger-Müller detector. This is the one that does the clicking. And I've got a cloud chamber, which is the chamber that I built here, and that's what we were looking at for the last half hour or so. I'm not going to be describing in detail how I made it. That, in principle, will be a half-hour short talk, maybe another day. So I'll be showing you how we use it, but not necessarily how I put it all together. So let us kick off. So let me switch back to the video temporarily. So what are we looking at? We're looking at what most people would call a Geiger counter. Physicists don't like that word. Physicists prefer a Geiger-Müller detector, but that's just me being pedantic. Everybody else calls them Geiger counters. And it's counting particles that are coming into this room. Every click signals the passage of a charged particle coming from somewhere and going through this detector, which I'll say more about later, and the meter there is telling you that they're coming in at the rate of 1 a second, or 1 every few seconds, or something like that. Okay, we're going to get bored of the clicking after a while, so let me just mute the clicks and jump back to the PowerPoint. Okay, so what is that clicking? So as I've just said, each click signifies a charged particle, a subatomic particle. We're not talking about atoms, we're talking about the constituents of atoms coming through the detector. So as I've said, to be pedantic, we shouldn't really call it that, but we're going to continue calling it a Geiger counter. And the Geiger counter does its job of simply counting what's coming through, the rate at which particles are arriving. So what are these particles? Well, maybe these particles were spat out from an atom that's lurking somewhere in this room. Maybe the particles that we are detecting with these clicks have actually come from a more distant origin. Maybe they've come from a supernova that went off a long time ago in a galaxy far, far away. But the Geiger counter can't tell us that. The Geiger counter just clicks to tell us something has arrived. It'll tell us the rate of radiation arrival. It won't allow us to identify what type of radiation that is. We'll need something else if we want to be able to identify them. So we are going to be talking initially about background radiation. And some of you know all this, but I'll tell you anyway. Radiation is around us all of the time, okay? You've lived with background radiation all of your lives, and it's not necessarily anything to fear. Before dealing with cosmic rays and cosmic radiation, I'll just be giving the context by talking about radioactivity from the Earth. And the one thing that you have to remember is basically that in a nutshell. The Earth is radioactive. So although you think of radiation and radioactivity as being scary, we are living on a planet that is radioactive. It's always been that way. In other words, apparently. The Earth was radioactive when it was made, 4.5 and a bit billion years ago, and it's been radioactive ever since. It is a natural consequence of the elements that make up the Earth. If we have a look at all of those elements, of course we have dozens of different elements that make up the Earth, the crust of the Earth as well as the interior of the Earth. We catalogue them, if you like, in the periodic table of the elements. Now, some of the elements in the periodic table are stable. In other words, when you make an atom of some things, that atom lives forever. You might be able to add an electron or take away an electron, but basically the atom lives forever. It is stable and will not change. But there are some atoms in the periodic table that are unstable. In other words, they don't like being what they are. They want to change into something else. Physicists talk about decay. That doesn't mean they go moldy and they last longer in the fridge. Decay in this context means they change into another element. So when I talk about a particle decaying or an atom decaying, I'm talking about it changing. And in the process, the nucleus at the heart of the atom emits something, some subatomic particles. And we can start to visualize that by asking ourselves, well, what can we see if we look at a few samples? We're not going to start with bananas. I'll leave bananas till a little bit later. We're going to start with, let me just switch back to the live demonstration, and we are going to look at radioactivity. So we're coming back to the Geiger counter. Let me just put the noise back on again. We're going to have a look at a particular piece of glass. It's a piece of glass that you probably can't see, but it's a slightly greenish color. And this particular piece of glass, it looks a little ornamental, but if I bring it up to the Geiger counter, I think you can see that it's producing something above the background rate. This particular piece of glass has had uranium added to it because it makes it a nice green. And also, it has another characteristic which Sue will just help me demonstrate. You don't need to see the details of this particular piece of glass, but if she holds up the piece of glass, the reason people put uranium in glass is because it fluoresces. And if you walk closer to the audience, they can see just how bright that is. So that's why people put uranium. It's nothing to do with the radioactivity. It's because it fluoresces under ultraviolet light. So you put this in your cabinet and you switch the UV lights on, you get a very nice, attractive display. Thank you very much, Sue. So that's a little bit of an aside, because although it is radioactive, that's not why people buy it. And just for the benefit of anybody watching the video, what I've just shown the audience is the fact that a piece of uranium glass under UV light fluoresces like mad, as you can see from this piece there. Okay, let's come back there. Right, that particular piece of glass, in principle, is radioactive, but I can't fit that in my cloud chamber. So we're going to have to find something else. So I am going to find a radioactive sample. It's a piece of uranium that was dug up somewhere in the world. And with a little bit of care, I'm going to place it inside the cloud chamber. At the moment, you're seeing just cosmic ray background radiation. But in a moment, I'm going to place a radioactive sample in, and we will see what a radioactive sample looks like, if I can do this without dropping it. I've just disturbed the cloud chamber, which means the alcohol that's in there that's forming the clouds has been disturbed, and it will probably take just a little bit of time for everything to settle, and the drizzle that you can see, the clouds forming in the cloud chamber, that will allow the passage of a charged particle to be visible as a contrail, as a condensation trail. It might take just a minute or so for that to settle back down so that we can see. Again, let me just switch off the Geiger counter to avoid the annoying clicking. So somebody shout when they see something coming from the little piece of rock. This little piece of rock is called studite. It doesn't really matter what it's called, but it contains a little bit of uranium. And that uranium, oh, just when I turn my back on it, yes. So you might still see the occasional cosmic. You can tell these aren't cosmic because they're coming from the rock. You can see the tracks appear to be touching the rock. If you see a track in the middle of nowhere that doesn't appear to be touching the rock, that is just a cosmic which will always be there. But, okay, you can now see that that rock is kicking out something. Yep, undeniably, that rock is producing something which is flying through space and flying through the cloud chamber, leaving condensation trails behind it. This wasn't quite how radioactivity was first discovered, but very early on, over 100 years ago, this is how people looked at what charged particles are actually. Whoa, look at that. That's about 6 or 7 at a time there. It's only a tiny little thing. It's only a few millimeters in size. For those that haven't actually seen the cloud chamber, this is approximately 4 centimeters by 6 centimeters. So we're only talking about something that's less than a centimeter in size, but it's got a fair bit of uranium in it, hence it's spitting out an awful lot. But we can ask ourselves, well, okay, it's spitting out something. Definitely it's spitting out something. We only need to watch it for a minute or so to be convinced it's spitting out something. But what exactly is it spitting out? Okay, having put it down, I've now forgotten where my pointer is. Okay, so let's just jump back. We've done the live demonstration of radioactivity. And in true Blue Peter fashion, I filmed a different rock sample a while ago, just in case the live demo didn't work as well as it should do. This is a different rock. This is a rock called Boltwoodite. Again, it contains some uranium. Again, you can see tracks coming out. Occasionally, you see cosmics in the background, but you can definitely see tracks. I took a video over a minute or two, and then after that, I took the video, went through it, and picked out the frames that seemed to show a nice track. And there were 20 of them. And then I simply made a composite image of all the tracks. So that, if you like, is a sort of a time lapse, if you like, of lots of tracks coming out of that radioactive sample. The first thing you might notice is they fall into 2 camps. Some of them are very narrow and barely a pixel or 2 wide on this particular camera, and some of them are very broad and very ghostly. So you can see these in the background. That one, for instance, that seem to be very broad but relatively ill-defined compared to the very bright, very narrow electron tracks. So clearly the radioactive rock, is emitting something. But what are the particles that are coming out of that rock and going through the cloud chamber and leaving tracks? Where do they come from? So we're now going to discuss radioactivity. Again, this is not a physics lesson, so I'll just do the bare bones. An atom, according to our understanding, is basically a charged nucleus in the middle, a positively charged nucleus, and lots of negatively charged electrons buzzing around like a hive of bees. But when it comes to radioactivity, even though we might talk about electrons in radioactivity, it is only the nucleus that is responsible for the radioactive properties of an atom. The electrons do not have any part to play, or essentially no part to play. So it's what the nucleus of the atom is doing that determines the radioactivity of the atom. So what could a nucleus do? And a nucleus is a collection, it's a whole bag of 2 different types of particles called protons and neutrons. Protons are charged, neutrons aren't. So if we imagine a very big nucleus, perhaps that is the nucleus of maybe uranium or something like that, how could a large bag of protons and neutrons, how could that particular nucleus decide to change? Well, it might decide to spit out a proton. Maybe it's unhappy having that many protons. Maybe it wants to get rid of one, so it might spit out a proton. Maybe a nucleus is unhappy and really doesn't like the number of neutrons it's got and wants to spit out a neutron. That's a possibility as well. If it's got really far too many protons and neutrons, it might decide it's much happier by kicking out 4 at a time, 2 protons and 2 neutrons. That particular collection of particles is called an alpha particle, otherwise known as the nucleus of a helium atom. And there are other possibilities. The nucleus might decide to spit out so-called beta particles. They're called beta because at the time people didn't know what they were. We now know that beta particles, if they have a negative charge, we know that those are electrons. If these beta particles have a positive charge, we know that they are anti-electrons. They are antimatter. Electron is part of matter. A positively charged version of the electron is an anti-electron, sometimes called a positron, and that is a particle of antimatter. And one other possibility is that the nucleus might decide it's unhappy and wants to kick out a photon of electromagnetic radiation, and that will be a very high energy photon. It won't be light, it will be something more like gamma rays. Okay? So there's lots of ways a nucleus could decide to spit out different particles. I am not going to discuss all of those in detail. I'm just going to say that the most common ones, which you might have heard of, are called alpha and beta and gamma radiation. So they're the most common types. Alpha particles, otherwise called alpha rays, again for historical reasons, when they were first discovered, people didn't know whether they were rays, as in light rays, or particles, as we would understand them today. So they're sometimes called alpha particles, sometimes called alpha rays. They are the same thing, they're just two alternative names. They are made up of 2 protons and 2 neutrons, so they are effectively the nuclei of helium atoms. Beta particles, as I just mentioned a moment ago, they're called beta rays or beta particles. They are effectively electrons, or possibly their antimatter equivalent, anti-electrons. They are relatively lightweight. They're much lighter than alpha particles. Alpha particles are basically bulldozers. They are so heavy. Electrons are much, much, much lighter by thousands of times, and they can penetrate further than alpha particles through the air. Gamma radiation is different from alpha and beta because gamma is quite definitely electromagnetic rays. It is not a particle unless you want to think of it as a photon being a particle of light. That's perfectly okay, but it is electromagnetic radiation, whereas the other two are bits of stuff, protons and neutrons or electrons. So that's what we've got, alpha and beta and gamma. So let's switch back to what we were looking at and re-examine what we just said. We're looking at alpha and beta radiation. For reasons I'm not going to go into, we do not see any gamma radiation in a cloud chamber. So any track which is nice and small, possibly a little bit zigzag, is an electron. They've all got quite a lot of energy, so most of these tracks look relatively straight. But alpha is more of a bulldozer and will produce a much broader track, hence the track not being a nice narrow line, but being a broad track, because the alpha particle is so massive compared to the electron being thousands of times lighter. So we can actually identify, just by looking at the tracks, what sort of particles are actually coming out of this radioactive sample. And again, rather than spend all our time watching that, let me go back to PowerPoint and say this is one I prepared earlier, and again we see very narrow tracks coming from beta particles and very broad tracks coming from alpha. Whilst you're watching that, I will just take the sample out because I don't want it there for later. Okay. So again, the ghostly tracks are alpha particles, the bright narrow tracks are beta particles. That's true for a sample which is radioactive. It's also true for cosmic rays. If we see a very narrow track, that's probably a beta. If we see a very broad ghostly track, it's probably an alpha. So as before, I took all of the individual tracks and put them all together so we can again see the difference between the two. Right, atoms come in various flavors, or cousins if you like. If we take a given atom, then depending on how many protons and neutrons are in the nucleus, we get cousins that we call isotopes. So to take an example, a specific example to try and illustrate that, if we take a nucleus in which there are 6 protons, element number 6 is what we call carbon. Carbon is just a label we use for the element that has 6 protons in the nucleus. It's just shorter than saying the element that has 6 protons in the nucleus. If a carbon atom has 6 neutrons as well as those 6 protons, we call that carbon-12 because 6 protons plus 6 neutrons, the total number is 12. We call that carbon-12. And carbon-12 is stable. Basically, you are made of mainly carbon-12. But there's another type of carbon. If you take a carbon atom that has not 6 but has 8 neutrons in the nucleus, 6 plus 8 is 14. We call this one carbon-14. This particular isotope, this particular cousin of carbon-12, is radioactive. It is not altogether happy having that combination of protons and neutrons. It wants to change into something else. It is radioactive. It is unstable. This is the particular isotope that's responsible for carbon dating. Every organic system will have a lot of carbon-12 and some carbon-14, and we can tell how old it was, in other words, when it stopped absorbing carbon, by looking at the ratio of C12 to C14. So the idea of isotopes, remember, we've got a periodic table with lots of elements, but a lot of those elements will have radioactive isotopes. Even carbon, which everybody thinks as being perfectly okay because we're made of carbon, even carbon has radioactive isotopes. What are the main radioactive elements in the periodic table that we're likely ever to come across? Well, one of them is potassium. It's one of the most abundant of the radioactive elements. In your body, if you're healthy, you have a fair bit of potassium in your body. In fact, if we work out the radioactivity of potassium and the amount of potassium in your body, there are probably 4,000 atoms per second decaying into something else and emitting radiation from inside you. So in other words, you are radioactive. There's no point being afraid of a radioactive source if you're actually emitting more radiation than the source itself, and that could indeed be the case. Potassium is one of the largest contributions of natural radiation. The second one that exists in nature is thorium, and that's more abundant even than uranium, even though you've probably heard of uranium and maybe haven't heard of thorium. Thorium is more abundant than uranium, and uranium is more abundant than you think, probably. If you think uranium is a very rare element, no, it isn't. There are 3 parts per million in the Earth's crust. That's 500 times more than gold. So, in other words, the only reason we dig gold out of the crust rather than uranium is it's easier to dig gold out of the Earth's crust. There is far more uranium. It's not necessarily in a part of the world that we have easy access to, but there's a lot of it in the Earth's crust. In the Earth's core, these elements that are radioactive, they're not just in the Earth's crust, they're in all of the Earth. These radioactive elements have been emitting radiation for billions of years, and they have been keeping the Earth's core hot. They've been keeping the Earth's core molten. The Earth's core being molten is nothing to do with radiation from the sun. It's all to do with internal radiation from these radioactive samples. So they have been keeping the Earth's core molten. A molten core that's rotating gives you a magnetic field, and lo and behold, a magnetic field helps protect us from radiation from space. So there's the circle of life, if you like. Radioactive elements are responsible for protecting us from radiation. It's a little bit ironic, but there you go. And just as a little bit of an aside, a very small fraction, 0.01% of potassium, is a particular isotope. Remember, that means it's a particular combination of how many protons, how many neutrons. A particular isotope of potassium emits beta plus radiation. Beta means something like an electron, but beta plus means it's got the opposite charge to an electron. An electron has negative charge, so a beta plus is a positron, or a particle, if you wish, of antimatter. That means that anything that contains potassium is an antimatter producer. And of course, any food rich in potassium will emit antimatter. That means Brazil nuts are very rich in potassium. Bananas are very rich in potassium, which means as we stand, this banana is emitting some antimatter, and not much of it is going your way. You don't have to panic. The amount that's coming out of one banana is tiny, but it does produce antimatter, as well as Brazil nuts and at least a dozen other foods that are rich in potassium. And because bananas emit radiation, some time ago people said, well, why don't we have a unit of radiation that's relative to bananas? What about the banana equivalent dose? Instead of talking about REMS or RADs or all these other units that nobody knows about, why don't we just compare it to the radiation from a banana? It was done somewhat jocularly, but actually it proves to be quite useful in a sense. It's how much are you receiving in any given dose compared to the dose you would get from eating one banana. So for instance, compared to eating one banana, what is the dose that all of you are getting, everybody, every day, from cosmic rays? They're coming everywhere. You're not protected by the roof or the walls. Cosmic rays are coming through, and you are receiving a dose of cosmic rays all the time. Compared to eating one banana, the amount of cosmic rays you're receiving is something like a dozen bananas. There we go. So that's why the banana equivalent dose exists, just to give you a comparison. And by the way, it wouldn't be a dozen bananas if you spend a lot of your time flying, because you're closer to the cosmos when you're in an aircraft flying at 10,000 meters or more, and therefore you will be closer to the source of a lot of radiation, as we will see shortly, and so your dose of cosmic rays will be higher. That's why airline pilots have to be careful as to how many trips they take in a year. Finally, before coming back to the main topic of the talk, one other source of radiation that's terrestrial is radon. Not all radioactive elements are solid and dug out of the ground. Radon, for instance, is a gas. It's produced by the radioactive decay of the uranium that's in the ground. So if there is uranium under our feet, that will produce radon. Radon's a gas. It won't stay in the ground. It'll bubble up, and eventually it'll be in the air. And if we look at where we're likely to see radon, this is a map of radon concentrations in the UK. And if you're trying to work out what the red actually means, if you think about it, those are the relatively mountainous areas. Okay? Uranium tends to exist in granite. If you have granite under your feet, that granite will contain some uranium, and that uranium will produce some radon. So you can see the Pennines and Cambria, and especially Devon and Cornwall, are very rich in granite, so they have high levels of radon. Where I live, on the Wirral, very low. Where we are at the moment, which I think is somewhere around there, again, relatively low, perhaps as low as it could be. That doesn't mean zero, that just means not as high as other parts of the country. There will be radioactive atoms of radon in this room. I calculated earlier that given the size of this room, there are probably 1 billion atoms of radon in this room. That sounds like a lot, but it's absolutely tiny, because the number of oxygen and nitrogen molecules in this room is a million or so. The amount of radon is absolutely tiny by comparison, but it is there, and we can see it in the cloud chamber. Radon gas emits alpha particles. So if we see an alpha particle in the cloud chamber, it's coming from radon gas. Anything outside the cloud chamber can't get through the glass, so it's the radon inside the cloud chamber that we see when we see an alpha particle when we get back to the cloud chamber. So that gives you a sort of summary of where we stand with terrestrial radiation, to give you the context of, okay, alpha and beta and gamma radiation is all around us, usually at very, very low levels, but that doesn't stop us seeing it if we put a sample of rock, for instance, in our cloud chamber. So now let's return to the main topic and think about cosmic rays. The pioneers in the turn of the last century, at the end of the 1800s, early 1900s, these were the pioneers. I'm guessing that everybody will have heard of Marie Curie. You may not have heard of Becquerel or Hess. Becquerel discovered radioactivity. He looked at photographic plates and found that they were getting fogged if he left them in the same drawer as the uranium compounds. Why would that be? He discovered radioactivity. Marie Curie then refined various elements and purified elements, including, for instance, polonium and radium. Hess basically discovered cosmic rays, and we'll see how he did that in just a moment. So in the late 1800s, people were doing lots of experiments trying to understand how radiation worked. They used so-called gold leaf electroscopes. What are these? They're little jars, little bell jars, and inside there's 2 leaves of gold. If you charge them up by taking a cat and rubbing it against a balloon, or vice versa, so that you get a little bit of charge, remember, positive charges repel, opposites attract. So if you charge both of those gold leaves with the same charge, they will separate because they want to be apart from each other. But what they found was if they charged up an electroscope like this, as they watched it, the leaves would come together. In other words, they would discharge. Where does the charge go? They've isolated it. They determined that some charged particles are zooming through their electroscope and discharging their devices. So they determined from simply what those gold leaves are doing, they determined that there was such a thing as background radiation. But the big question was, well, is it coming from above or below? We know the radiation is there, but where's it coming from? A physicist called Theodore Wolff in 1910 said, I know, I can tell if it's coming from the ground or somewhere else. I'll do a measurement on the ground, and then I'll do the same measurement on the top of the Eiffel Tower. Perfectly sensible thing to do. If it's coming from the ground, you would expect the radiation to be less at the top of the Eiffel Tower. But the radiation decreased, but not by as much as you would expect. It's as if it perhaps was coming from the ground, but something was confusing the issue. It's not going down as much as you thought, so maybe some radiation is coming from the sky. Is it possible that the tower is radioactive? That's not a silly thing to think about, because the tower is made of iron. Iron is dug out of the ground. If the ground's radioactive, maybe the Eiffel Tower is radioactive. And what's the atmosphere doing? We know radon exists. Is it possible that radon is actually affecting the results? This is where Hess stepped in and said, you can't tell from going up the Eiffel Tower whether or not it's coming from below or above. If you want to tell the difference between radiation from above or radiation from below, you need to go up much higher than the Eiffel Tower. So he designed detectors that could work in a hot air balloon. And then he said, right, I'm going to do various flights to various heights, and then I'll really see whether or not the radiation goes up or radiation goes down. So in 1911, 1912, he's the guy in the hat there in the middle. Hess did a number of pioneering balloon flights. Firstly, he went to 1,000 meters, and the radiation levels didn't change much, which is why there was confusion on going up the Eiffel Tower. It just wasn't high enough. But then he tried going up to 5,000 meters, and bam, the radiation levels increased significantly. He proved that the radiation is mainly coming from up there, even if a little bit is coming from the ground. But was the increase due to, for instance, something coming from the sun, or was it something coming from beyond the sun? How are you going to tell? Well, the easiest thing is to say, well, fly at night. Because the sun is below the horizon, any radiation from the sun won't be reaching the balloon. But who wants to take a hot air balloon flight at night where you can't see where you're going? Crazy idea. Hess had a wonderful idea. If you want to block radiation from the sun, but you don't want to fly at night, pick a day with a solar eclipse. Fantastic idea. He went up, waited for the moon to cover the sun. When the moon covered the sun, the radiation levels didn't change. So it is not coming from the sun, or at least only a tiny amount can be coming from the sun. This radiation that is responsible for discharging their electroscopes is coming from the cosmos, not just from our neighborhood of the solar system. In 1936, Hess was awarded the Nobel Prize in Physics for the discovery of cosmic radiation. So cosmic rays was a term that was coined at about this time, just a little bit before he got his Nobel Prize. Okay, so now we know that cosmic rays are coming from beyond the sun. We now know that they are actually particles that are coming from some source which we'll deal with later, and when these particles hit the atmosphere, they produce a shower. In other words, there's something coming in from outside the Earth's atmosphere. When it hits the Earth's atmosphere, whatever these particles are, they smash into oxygen or nitrogen or whatever else they can find, and they produce a cascade of secondary particles according to this sort of artist impression. This cascade of secondary particles is called an air shower. In this particular case, there were two air showers, which I think is a little bit confusing. Generally speaking, you'd only expect one air shower at any given instant. So this is just an artist taking a little bit of license here. If we have a look on the right-hand side, that's a schematic of an air shower, but it doesn't show anything like the number of particles that are generated. It's a much simplified diagram, but it shows what's happening. Primary cosmic rays, in other words, something traveling through the cosmos, is arriving at Earth, it hits the atmosphere, and produces a whole load of secondary particles. At each point, when secondary particles are produced, and then more, and then more, and then more, at each level, if you like, every new set of particles that are created share the energy of the incoming particle. And a cascade, unlike this diagram, a cascade won't necessarily produce half a dozen particles arriving at sea level. It could produce thousands or even millions of particles. One particle coming in, if it's energetic enough, could produce millions of particles by the time they reach sea level. What sort of particles might be produced? Well, some of the particles are the familiar ones we know about. We know atoms are made of protons and neutrons and electrons. Well, some of the particles that make it to ground level are the familiar ones of protons and electrons. But some of the particles that make it to ground level are rather less familiar. They are unstable and don't live very long. They might only live for a fraction of a second. For instance, one of the particles that we're going to see, if you haven't already seen in the cloud chamber, is a particle called a muon. It has no part to play in atoms. It is nothing to do with how atoms are made. It's nothing to do with how you are made or anything else that is made of atoms on the Earth. It's a particle that is made by cosmic rays, and it only lives for a tiny length of time. It happens to be rather more massive than an electron. That's why in a cloud chamber, when we see a muon, it is so massive, 200 times more massive than an electron, it tends to go in a straight line, whereas electrons tend to zigzag like in a pinball machine. A muon won't live for more than a few microseconds. So even though we see them in a cloud chamber, they have only lived for a few microseconds and then will effectively die. They will decay into something else. But a few microseconds is long enough to reach ground level. And therefore, it is possible to see muons at ground level. It is possible to see them in a cloud chamber. And that's one image of one video I took where I was taking a video over a few minutes, and I picked out what I think is a muon. It's a straight track. Electrons tend to be much more wiggly than that. So that is a cosmic ray muon. And as I say, it was born a few microseconds ago, and then it goes through the cloud chamber and leaves a condensation trail, just like an aircraft flying through the sky. What are the particles that actually hit the atmosphere? Up till now, we've said protons and electrons and muons are the ones we see at sea level. What is the particle that actually hit the atmosphere in the first place to produce the air shower? In other words, what are the so-called primary particles, the one that created the air showers? Well, again, decades of research have told us what those particles are. Most cosmic ray particles, 90% of them, are protons, the lightest positively charged particle other than positrons. So the nucleus of a hydrogen atom, in other words, take a hydrogen atom, strip the electron off, that's what you're left with, a proton. Most cosmic rays appear to be protons. 9% of them are this other particle that we've already heard about, alpha particles, or if you prefer, the nuclei of helium atoms. So they're obviously a lot heavier because there's 4 protons and neutrons being very similar in mass to protons. So there's 4 times the mass there. The remaining 1% are all the other nuclei that exist. In other words, the nuclei of lithium or beryllium or boron or carbon or nitrogen or oxygen or all the way through the periodic table. So only a tiny number of them are these very heavy nuclei, and they're all the same nuclei that we find in the solar system or we find on Earth. In other words, all of the varieties of the elements, but most of them are protons and alpha particles. That's 99% of cosmic rays that hit the atmosphere. So let's have a think about how it is that we actually detect these cosmic rays. We've seen how they were originally detected. Gold leaf electroscopes, very simple, get a little bit of gold leaf. Gold leaf is used just because it's very light and any positive charge makes the leaf separate, and we can easily see whether those leaves collapse to see whether we've got radiation. Not so good for telling what the radiation is, but very good for the early pioneers. But we are talking about this beastie. Let's just think about how that works. So I said this is a Geiger counter, or more correctly, a Geiger-Müller tube. And if we see what's going on inside that tube there, what we've got is a load of gas, usually an inert gas like neon or argon or something like that, maybe helium. And incoming radiation ionizes some of the atoms in the gas inside that tube. And the ionization produces positive and negative charge. And if we put a high voltage on a probe in the middle and a probe on the outside, as soon as we generate positive and negative charge, we get a current flow. As soon as we get a current, the yellow box changes the current into a click, basically. It amplifies it and sends it to a loudspeaker so that when we get one incoming photon or particle of radiation, we get one click in the Geiger counter. What about this other marvelous invention that's sitting next to it, the cloud chamber? Well, back in the late 1800s, Charles Wilson was supposedly inspired by the sight of the Brocken spectre from the top of a mountain. He went up Ben Nevis and he saw the Brocken spectre, an atmospheric phenomena that you see when the sun is behind you on particularly misty days. And he thought, wouldn't it be good to study this? And I don't want to study it on the top of Ben Nevis. How do I make clouds in my laboratory? So basically he invented the cloud chamber. Back in 1911, he tried to figure out how he could make clouds in a small jar. But it wasn't long after inventing this particular beastie to make clouds in a jar that he realized that every once in a while he saw a track go through his cloud chamber. He saw tracks of what could only be charged particles that are leaving a condensation trail. In other words, it was fairly quickly after the invention that he realized that charged particles passing through a cloud chamber left tracks, and basically the tracks gave you some clue as to what type of particle it was. The particle physicists who are interested in smashing atoms together and seeing what comes out of atoms were delighted at the idea of having a device in which they could actually see particles moving. Rather than just assume that they existed, they could now see particles and they could see interactions and they could see things move and they could see things bend in a magnetic field and do all sorts of experiments. In 1927, because of this invention, he was awarded the Nobel Prize for this wonderful quote, "the most original and wonderful instrument in scientific history." That shows you how important the cloud chamber was in terms of the development of our understanding of the world around us. Now, the 1911 cloud chamber has changed slightly because that's what it originally looked like from Charles Wilson, and this is my version of it in 2024. But essentially, it does the same job. Mine, I'm not going to talk about the design, but mine is based on the idea, no, it's not a cafetiere, but if NASA ever decided to land a cafetiere on the moon, I think that's what it would look like. Basically, it's a jar which has alcohol at the top soaked into that sponge, and if you heat the top, the alcohol evaporates and the bottom is kept cold. So it'll evaporate at the top, it'll condense at the bottom, so it starts to form a sort of drizzle of droplets which eventually rain down onto this cold plate at the bottom. The cold plate is what you see here, this sort of rounded cornered rectangle, so that's where all the action is in a cloud chamber. The rest of it is just to make the alcohol vapor which eventually will condense down here and produce tracks. So again, we can switch back to cosmic rays. I've taken the radioactive sample out, so we should be back to cosmic rays again. There, you see one? Yep. Everybody, there's obviously some pulsation in the background. Just try and ignore that. But every once in a while, there seems to be a little bit of liquid condensing on the side there as well. But every once in a while, you see a track go through. That is one of these cosmic rays. Remember, the cosmic rays that make it to ground level are probably muons, these things that don't make up atoms, or electrons or protons, which are the familiar bits and pieces of atom. So we haven't yet said where they come from in the first place, but every once in a while, let's just, whoa, that was a nice one. That was probably an electron because it wasn't particularly straight, it was slightly curved. Let's just watch it for a few seconds and see what else comes along. I'll switch back to this at the end of the talk, and I'll invite you to come and have a look at it for real rather than look at it on the screen if anybody wants a closer view. So a little bit of pulsation in the background, but other than that, hopefully, yeah, there's a short track there from probably an electron. Let's see if we can get a nice muon come through before I finish waffling. Come on, there must be something nice around the corner. That's it with the universe. You can never get it to perform. Or it's like buses. You wait ages and then 3 tracks come along at once. There was something coming through there. Come on, let's have a nice one before I switch back. There was something down in the bottom right corner, but not particularly spectacular. Another one down the bottom there. Maybe it's not going to play ball. We obviously got a nice one earlier. Okay, like Basil Fawlty, I'll give it a damn good thrashing unless it works nicely. And oh, there's a little electron coming off the side there. Oh, that was a nice one. Okay, a nice track there. So let's just... So we can definitely see these particles, these so-called secondaries. Something hits the top of the atmosphere, produces a shower. Some of them make it to ground level. We can see those, and we can tell the difference between alpha particles and muons and electrons just by looking at the physical characteristics of the track. Are they very broad? Are they very narrow? Are they very wiggly? Are they very straight? So we can tell the difference between these things. And again, Blue Peter fashion, I took a video just in case the demo didn't work too well. And this is a video of a few different tracks. That was quite a nice bright one on the right-hand side. That was probably a proton. Here we've got a few electrons coming through, and an electron on the left, and another electron, and another electron. If they're not straight, they're electrons. And as I say, the one we saw earlier that was very straight, that was probably might have been a proton in the top left, very bright. That was probably a muon. That's probably an electron. So again, if we wish, we can take a video, which is this is what I did when I was testing it. I took a video. That was a nice electron, a nice wiggly track there. I took a video, and I went through that video, a nice electron, a big horseshoe U shape there. I took a video and then sat down and went through it frame by frame. That was probably a proton, a very bright track there. I went through it frame by frame and picked out every frame of the video I could find that seemed to have a nice track on it. And then I made a composite image of all of these tracks superimposed on each other. And that's what I saw in about an hour. Lots of wiggly things in the background are electrons, these really bright ones on the right and the left of the screen there. They're bright enough that they're almost certainly protons, positively charged, making large contrails. A few muons are in there, but they're difficult to see because there are literally hundreds of tracks taken over this, probably best part of an hour or so. So if you have the patience, you can see all sorts of particles going through the cloud chamber if you just sit and watch them. And again, I invite you to come and have a closer look after the talk is finished. There have been lots of cosmic ray experiments since Hess first discovered cosmic rays 100 or so years ago. For instance, cosmic ray detectors were put onto the Voyager probes because we didn't know what cosmic rays are out there. We had an inkling as what cosmic rays arrive at Earth, but how do they differ when we go out into the solar system? So they put a cosmic ray detector on the Voyager spacecraft and monitored the cosmic ray counts, if you like, how many cosmic rays were seen as Voyagers flew through the solar system. In 2012, Voyager 1 was deemed to have left the solar system because the number of galactic cosmic rays, the number of low energy rays coming from the sun went down, and the number of high energy rays from the rest of the cosmos seemed to go up, implying that it had left the influence of the sun. So that's the point at which they said it's entered interstellar space. Voyager 2 isn't going quite as fast as Voyager 1, it's about 10% slower, so it took longer for Voyager 2 to come to the same conclusion that it had left the solar system. It was something like 6 years later in 2018. And if we have a look at its cosmic ray detector, the bottom trace is how many low energy particles are we getting from the sun. In November 2018, it fell through the floor. Whereas the number of high energy rays that were determined to come from beyond the sun went up and then took a little bit of a kick when this number fell. In other words, it's determined that that point there in November 2018 was the point at which Voyager 2 left the solar system. It's a not exactly arbitrary definition, but it's a good point to say when the number of galactic cosmic rays goes up and the number of solar cosmic rays or cosmic particles goes down, that's the point at which we say it left the influence of the sun. There's other cosmic ray experiments around. For instance, there's one on the International Space Station called AMS. That stands for Alpha Magnetic Spectrometer. You can see the size of it compared to the astronaut in the top left who's there. It's a big thing, and its job is to basically monitor how many cosmic rays are arriving. Of course, the ISS is essentially above the atmosphere. It's very thin air up there, so it's essentially above the atmosphere, so it's monitoring how many primary cosmic rays are arriving. There are also a lot of observatories looking at the secondaries, not trying to work out what's going on at the top of the atmosphere, but trying to determine that based on what they can see at the bottom of the atmosphere. In other words, if an incoming particle produces a shower, there's an artist's impression here of the shower, if you have enough detectors on the ground to pick up as many of those secondary particles as possible, then you stand a chance of trying to work out what this shower looks like and determine what it was that actually hit the atmosphere in the first place. One of these biggest observatories is called the Pierre Auger Observatory in Argentina. And if you do want to catch as much of that shower as possible, given that the shower might spread over many, many kilometers, you can't afford to have a cloud chamber which is 6 centimeters by 4 centimeters, which is what our cloud chamber is. You have a much, much, much larger area detector. And this one in Argentina has a set of detectors spread over an area roughly the size of Luxembourg. That gives you an idea. So these detectors here are spread over a huge area in Argentina. These detectors are tanks of water. How can you detect cosmic rays going through a tank of water? Well, because light gets slowed down as it travels through water, but these particles are going really fast, the particles are actually going faster than the light itself can travel through the water. And an analog of that is what happens when a solid object moves through the air faster than sound can move through the air. What you end up with is a shock wave, a sonic boom, if you have a particle moving faster than sound can travel. There's the optical equivalent of that. If a particle moves through a tank of water faster than light can travel through that water, you get the optical analog of a sonic boom. You get an optical boom, if you like. And that will work whether you're dealing with detectors that are looking for this optical light in water or whether you're looking in the atmosphere. And so if we imagine an incoming particle into the atmosphere, let's imagine a cosmic ray particle hitting the top of the atmosphere. What happens next? The optical equivalent of a sonic boom, a blue light. Sometimes called a photonic boom, but it's Cherenkov radiation or Cherenkov light. It happens in a billionth of a second, so it's a flash. It's not something that lasts, it's a flash. And so there's a whole load of telescopes, some of which are in Chile in the southern hemisphere and some of which are in La Palma in the northern hemisphere. And they are looking for this blue flash, which is characteristic of particles coming in, moving through the air faster than light can travel through the air. And so you get a blue flash, and you basically build lots of telescopes to look at the sky and look for the blue flash. There's a whole load of these telescopes being built in the Canary Islands and a whole load being built in the Atacama Desert. It's not finished yet, they've just started putting it together. One of my colleagues in the University of Liverpool is taking part in this particular project. The telescopes are all different sizes, you might notice. The brighter, the more energetic the cosmic ray that comes in, the brighter the flash, the easier it is to see. You only need a small telescope. If you want to see the lower energy cosmic rays that produce a much fainter flash, you need much bigger mirrors. So there's a selection of different mirror sizes because they've got different jobs to do. But this idea works regardless of whether you're dealing with particles traveling through water or particles traveling through the air. It works even if they're traveling through water that is solid, i.e. ice. So there's an experiment at the South Pole called the Ice Cube Observatory, the laboratory. The laboratory is sitting on top of the ice cap, but the detector itself, they've drilled down into the ice, there's the bedrock, they've drilled down in the ice and put thousands of photodetectors into a very large cube of ice, 1 kilometer by 1 kilometer by 1 kilometer of ice. That's why it's called Ice Cube. It's basically the biggest ice cube you can really imagine. There's the Empire State Building, just in case you're having difficulty with the scale. So it's a huge cube of ice, and just like water or air, if a particle travels through that detector faster than light can travel, you'll get a blue flash, and your photodetectors will pick it up. So here's a simulation of a particular event. If a particle comes in, it'll produce blue Cherenkov radiation, and those photodetectors will pick up that blue flash in a billionth of a second. And by looking at which particular photodetectors picked up the light, you can basically reconstruct where did this particle come from. You can basically backtrack the route it came in to the detector. And that brings us with the final point, which is where do cosmic rays come from and how do they gain so much energy? Just as a very quick aside, can we remind ourselves that Hubble, 100 years ago in 1924, came to the conclusion that if you look at variable stars, maybe they do have their use, if you look at variable stars, you can confirm that the spiral nebula that were thought to be possibly in the Milky Way are actually galaxies in their own right. They are found to be at a distance of order millions of light years, not thousands of light years. So this was first published in 1924. It'll soon be its 100th anniversary, if you like. This basically was the nail in the coffin of the great debate as to what are these spiral thingamajigs that we can see in the sky. No, they're not in the Milky Way. They are galaxies in their own right. So 100 years ago, the universe suddenly got an awful lot bigger because we then realized the Milky Way is not on its own. So if we start by saying if they don't come from the sun, remember Hess in the solar eclipse balloon flight determined that they don't come from the sun, do they come from the Milky Way or somewhere else? After Hubble made these observations in the 1920s, the question can be rephrased. Where do cosmic rays come from? Are they galactic coming from the Milky Way, or are they extragalactic coming from outside the Milky Way? It is thought that maybe the shock waves of supernova might accelerate particles to the sort of energies necessary to produce the cosmic rays that we see arriving at Earth. This, of course, is a loop of a video. This is not supposed to be implying that supernova go off and then again, and then again, and then again. Once they're dead, but the video is looping. And it is thought that shock waves, possibly from supernova, possibly from the jets of supermassive black holes, might be responsible for accelerating particles to very, very high energies. But we're not too sure, and we're not actually convinced of the mechanism. There's a few hypotheses as to how these shock waves might effectively accelerate particles. If we think about supermassive black holes, this is Hercules A, a galaxy at a great distance, the galaxy next to it, possibly about the size of the Milky Way, just to give you a sort of scale, if you like. The supermassive black hole in the middle of Hercules A, which of course is tiny, it's only about the size of the solar system. So on a galactic scale, the black hole is tiny, but the jets it produces actually go out of the galaxy and slam into the intergalactic medium and produce shock waves millions of light years away. So the amount of energy pouring out of that black hole is absolutely immense, and possibly the jets close to the black hole have the ability to accelerate particles to very high energies. So you might say, okay, there are some possibilities. Why don't we simply pin down where these cosmic rays are coming from? Surely working out where they're coming from should be easy. All we have to do is, according to this artist's impression, is have a look at a few air showers and say, well, it's coming from that direction, and if we look at a few different air showers, we can say, yep, that object there is producing these cosmic particles that are hitting the atmosphere. Unfortunately not. It's not quite that simple, mainly because of physics, gets in the way all the time. Charged particles get deflected by magnetic fields. So if you have a magnetic field, even though the particle appears to be coming from that direction, it might have actually taken a very convoluted route, and the source might not be where you think it is. The source might be somewhere completely different. Magnetic fields are everywhere. For instance, the magnetic fields around the Earth protect us from some of these charged particles, which is why charged particles end up spiraling around the Earth's magnetic field and get funneled towards the auroral zones at the North and South Pole. That Earth's field protects us from some of the lower energy cosmic rays. But unfortunately, it means that all cosmic rays, in principle, get deviated slightly by magnetic fields. Now, we know how to measure magnetic fields. We can just put iron filings on a piece of paper, and we can see the magnetic field from a bar magnet. How do we do that throughout the galaxy? It's tricky. But we can use dust as an indication. Dust, if you like, is like the iron filings that we've just seen. Dust can tell us what the magnetic field of the Milky Way looks like. And unfortunately, it's a mess. The magnetic field of the Milky Way is very complex. And simulations give us an idea of what it might look like. But if charged particles are going to be bending in these magnetic fields, and the magnetic fields are very complex, it's very difficult to work out where the charged particles have actually come from. And we think there are magnetic fields between the galaxies as well, but we don't really know. One saving grace might be that the laws of physics tell us that if you have a charged particle which is bent in a magnetic field, the higher the energy, the less the deflection. So if you have a really, really, really high energy particle, maybe it will hardly be aware of the magnetic fields, and it will travel in something close to a straight line. So even though we can't tell where the lower energy cosmic rays are coming from, if we look at the highest energy cosmic rays, that should be possible to trace back to their origin. So what sort of numbers of cosmic rays might we expect as a function of energy? I'll explain the energy in just a second. The units of flux are ridiculous, so I'll take those away. This is how many we would expect as a function of energy. I'll explain the scale in a moment, but we think the very lowest energy cosmic rays might be coming from the sun. A lot of them are coming from the galaxy, and we think the most energetic ones are coming from outside the galaxy. What's the scale down here? What are these silly units of energy? EV, what does that mean? Well, just to give you an idea, physicists use this particular energy unit. 1 EV is roughly the energy of a photon of visible light, okay? So the photons hitting my hand at the moment have an energy of approximately 1 on this scale, 1 electron volt. If we go to 1,000 times higher in energy, 1,000 times higher in energy takes us to X-rays. If we go 1,000,000 times higher in energy, we get to the sorts of energies of alpha and beta and gamma particles that we were looking at before in the cloud chamber. But cosmic rays are much higher, 1 billion, 1 trillion, 1 quadrillion times higher. Just to give you a sort of idea of scale, the particle accelerators here on Earth, the most energetic one at the moment is the Large Hadron Collider. That corresponds to this energy. If they get money, they might build an even more energetic particle accelerator, the so-called Future Circular Collider. That will be at the second arrow. But you can see that the most energetic cosmic rays are way more energetic than what we can produce here on Earth. How many might we expect to get as a function of energy? Lots at the low energy, very few at the high energy. Roughly speaking, at the very lowest level, perhaps low energy, we might get 1 every square meter of the Earth's atmosphere every second. The more energetic ones, 1 every square meter every year. So we're already getting to the point where they're getting a bit sparse. If we go to the really, really, really high energy end of the spectrum, 1 every square kilometer every year. So a very rare event. We wouldn't expect to get many. But these so-called ultra-high energy cosmic rays, these are the ones that should be so energetic, we should be able to figure out where they come from. This happened in 2021, the Amaterasu event. A particle came into the Earth's atmosphere with a humongous amount of energy. It was recorded by the telescope array in Utah. It was reported in Astronomy Picture of the Day a few months back, but it was actually observed originally in 2021. It's taken them a while to analyze the data. Some of the shower that was produced by this very energetic particle clipped the edge of this array, so they got enough data to work out what this was actually doing. Amaterasu, for those of you whose Japanese is not too good, Amaterasu is a Japanese sun god. It translates roughly to shining from heaven, which is a very nice way of thinking about these incoming air showers. Now, the Amaterasu event should not be confused with the tiramisu event, which is what they had afterwards when they realized that they had caught one of the most energetic particles ever. It's actually not the most energetic, it's the second most energetic particle ever discovered, the Amaterasu event. But they figured that it should be possible now to do something useful with that. It is such a high energy, surely it shouldn't be deflected by magnetic fields. So we should be able to trace it back and figure out what it came from. So all we have to do is to work out the geometry and basically ask, where does it point on the sky? They did that, and they found the direction points to, pause for dramatic effect, nothing. No supernova could be identified, no black hole in any galaxy could be identified as the source of this most energetic particle. So, I don't know, does that mean that it's not a supernova or a black hole? Does it mean it's something else? Or does it mean maybe the magnetic fields out there are stronger than we think, and the path of even this energetic particle is being deviated to the point where it seems to be coming from over there, but it's actually coming from over there, and we've got scrambled the information about its position. Basically, we need to spend more time observing more cosmic rays to get an idea of where they're coming from. I'll finish with this little analogy just to give you an idea of how energetic these things are. If things are very energetic, they will travel very close to the speed of light. The closer to the speed of light, the more energy they have. Just how close to the speed of light are these ultra-high energy cosmic rays actually traveled? Well, I've told you the Amaterasu event was the second most energetic particle. A few years earlier, some scientists saw the most energetic particle that's ever been observed to hit the Earth. It was so energetic they could not actually believe any particle could have that much energy. They called it the oh my God particle, and that's the name that stuck. it's something like 100 times more energetic than they thought was actually physically possible to fly through the universe. If we express its speed, calculated based on its energy, if we write its speed down as a fraction of the speed of light, it turns out to be 99.9999999. We're not done yet. 999. Not done yet. 999. We're nearly there. 995% the speed of light. There's no way you can get your head around just how close that is to the speed of light, but that gives you a taste of the fact that it must be really, really energetic if it's flying through the universe at that sort of speed. But there is a way of visualizing just how fast these things are going. Let's just imagine a race. Let's imagine we've got a racetrack that's approximately 100,000 light years long. So we've got a racetrack, hypothetically, through a vacuum, through a perfect vacuum, and the race is roughly the diameter of the galaxy. And it's a race between light and the most energetic cosmic ray that we've seen to date. They start at exactly the same time. Now, light, of course, will win. Nothing can travel faster than light in a vacuum. So the cosmic ray can't arrive first. The light will arrive first. But when the light crosses the finishing line, how far behind it is the cosmic ray that started 100,000 light years at the same point? How much ground has it lost in those 100,000 years, having traveled 100,000 light years? The cosmic ray will be behind the light photon by a distance equal to 5 millimeters. Having traveled 100,000 light years, it'll be 5 millimeters behind it. If you had a stopwatch and asked, after the light crosses the line, how long before the particle crosses the line, it will be way less than a nanosecond behind it. After 100,000 years, it'll only have lost a fraction of a nanosecond on light. That's how close to the speed of light it's traveling. An absolutely phenomenal speed corresponding to these phenomenal energies. So let me summarize. Cosmic rays are accelerated somewhere, somehow. We basically do not know. We think perhaps supernova are involved, perhaps the jets of supermassive black holes are involved. How else can you get a particle to those incredibly high energies unless it's these really violent events such as supernova or black holes? Cosmic rays are charged particles, so they will be deflected by magnetic fields. We think the low energy ones will have their paths scrambled. We hope that the very highest energy ones will travel in close enough to a straight line that we can get some idea of where they're actually coming from. Some of the lower energy particles will be caught by the Earth's magnetic field, which protects us from cosmic radiation. But some of the high energy particles will go straight through the Earth's magnetic field and will hit the atmosphere. Those that do hit the atmosphere will produce an air shower of secondary particles, and some of those secondary particles will make it to ground level. Not all, but some of them will make it to ground level. Those secondary particles are things like electrons and protons and these rather weird particles that don't exist in atoms called muons. So we get muons, electrons, and protons, and they make clicks in Geiger counters and they make tracks in cloud chambers. So when we see them at sea level, we see that sort of thing, and you saw them earlier before I started giving the talk. But just listen to those clicks. Essentially, all of those clicks are cosmic rays. There might conceivably be the odd bit of radon in there, but essentially all of those clicks are cosmic rays. Each click signals the arrival of a cosmic ray particle that might have started its life in a supernova in our galaxy, or possibly in the jets of a supermassive black hole in another galaxy. You're listening to the cosmos. Thank you for listening.